Okay, let's get started. Can you hear me in the back? Yes? Great. All right, let's see, announcements. I think the only announcement is that homework 1 is out. So if you haven't taken a look yet, make sure to go check it out. It's due in a little over a week. So make sure you go take a look at that. And come to office hours early if you, need help, because no one ever comes to office hours early. And then there's too many people at office hours right before the homework is due, and we can't help everyone. So take a look at it early. If you feel confused about anything, come to office hours early, and then you'll get better help that way. Okay, so let's start today's lecture. So we're back to linear regression today. We talked about this last Friday already. Remember least squares linear regression, also other forms like least absolute deviation, weighted linear regression, how all of these are related to MLE, right? So we've already talked about that, then why are we going back to linear regression today? Well, it's because we have some new tools to play around with, right? So this week we've been covering things like multivariate Gaussians, MVGs, and also how that can factor into a different type of statistical parameter estimation called map estimation, right? So using these new tools that we have, what we're going to do is we're going to go back and see if we can make some tweaks to our linear regression setup and come out with some new problem formulations. So remember, we've already motivated several linear regression formulations, least squares, least absolute deviations, weighted, from the perspective of MLE. Today, we're going to introduce 2 more formulations, and we're going to motivate them or try to understand them from the perspective of map estimation. And specifically, these are going to be called ridge regression and lasso regression. So perhaps you've already heard of these terms before. Perhaps you know what these are, you know what the solutions are, et cetera. Even if you know all of that already, maybe you can still get a fresh new perspective on how to interpret some of these problem formulations from the perspective of map. And time permitting, we'll also introduce this concept called featurization. Specifically, we'll talk about polynomial featurization, which will help us lead into next week's lectures. Okay, so let's get started with that. And to get started, let's actually recap a little bit what we did last time with map estimation, maximum a posteriori. So remember, in map estimation, what were we doing? Well, we were taking MLE, right, which is like the argmax over my parameters of the probability, the log probability of my observed data, right? And we were adding a prior onto the parameters. We were treating those as random and then adding a log p theta, right? So then the optimization problem that we ended up getting out of that looks something like this, right? We had, I'm skipping straight to argmin today, okay? So we're going to put a negative sign in front of it just to make it argmin. Remember, this is kind of like the perspective of maximizing probability versus minimizing a loss function, right? So it was an argmin over my parameters theta, right, over the sum of all of my observed data, right, the negative log probability of each data point, right? And remember here, now we put the theta over here on the right side of this bar because we're treating it as random, right? Minus this log prior term, log p theta. And remember, we said that the most common choice for this p of theta is this multivariate Gaussian, right, which is 0-centered and has some identity times sigma squared covariance matrix, where sigma squared is maybe something that we choose or remodel or just in general it's something that has to be specified, right? And this had the effect of favoring, right, parameters theta that are smaller in magnitude, that are closer to 0, right? The larger the magnitude, the less likely it is under p of theta, right? And so we can also write this out specifically for this choice of p theta. We can write this as, well, the first part stays the same, right? But if we choose, this MVG as our log p theta, then this term over here turns into 1 over 2 sigma squared. This is a plus now, right? Times the norm squared of theta. Plus some constant that doesn't depend on theta. So what we can do actually from this perspective, right? This is a minimization perspective. We can treat this whole thing inside the argument as my loss function, right? Or treat the whole thing inside the sum as my loss function. What we can do is we can actually give this thing over here, 1 over 2 sigma squared, we can give this a name. So let's say call this lambda. Why am I calling it lambda? Well, so the perspective is as follows. So when we're doing something like map estimation, what we're doing is we're assuming some model on our data, right? We're also assuming some model on our parameters saying that these parameters follow this distribution that's this MVG, right? And in that case, we might want to specify sigma squared. But we can also look at it, disregarding map for a second. This is also equivalent, right, to minimizing a loss function that has a regularizer in it, right? A regularizer in this case is something that restricts the magnitude of my parameters, right? So if I call this lambda, then basically what I'm saying is that maybe I can just think of it in terms of this coefficient directly rather than having to think about it in terms of sigma squared. So maybe I can pick lambda directly, right? So I can specify some lambda, and what it's going to do is it's essentially going to trade off between these two terms that I have in my loss function, this log probability or this negative log likelihood, right? And then this L2 squared of my parameters. So what happens as lambda gets bigger? Well, as lambda gets bigger, what I'm saying is that I care more and more about the magnitude of my parameters, right? And so what's going to happen is that the parameters I'm going to find are going to be closer and closer to 0 the larger that lambda is. Okay, what about if lambda gets smaller? Well, we don't want lambda to get negative because we don't want to encourage large parameters, right? But we can have anything greater than or equal to 0, right? And if lambda is 0, what that means is that I don't care at all about the magnitude of my parameters. I get back to MLE, right? I get back to something like least squares linear regression, where my parameters can take on whatever values they want, right? And so this has an inverse relationship with sigma squared, and oftentimes it's just easier to think about lambda directly rather than having to think about what's a good value for sigma squared. Okay, I didn't animate this slide. That's okay. We'll talk about it. We'll talk through it slowly, okay? So we can apply this idea, right, where we have this prior being this MVG, or equivalently what we call L2 regularization, right, because we're adding a regularizer in the form of the 2 norm squared, to least squares linear regression. Remember least squares linear regression, right? So what is the resulting learning problem? Well, here's least squares linear regression, right? Here I have W, right? But that's just my weight vector. It's the same thing as theta, right? So theta is the same thing as W. I'm just giving it a different name because that's the convention in linear regression, right? So we have trying to minimize over W this 2 norm squared between XW and Y, right? And if you remember how we got this, we can get this from the MLE perspective, right? Where we say that the outputs Y, right, conditioned on the inputs X, comes from a Gaussian, right, where the mean is a linear function parameterized by W, and then the variance is some sigma square that we don't have any control over, right? So that's how we get this minimization problem, minimizing the 2 norm squared of XW minus Y. So if we add L2 regularization, right, basically add this log p theta term, if you want to think about it from the map perspective, right, what we're doing is we're taking our original problem and then adding this lambda times the 2 norm squared of W, right? So this is going to say, find me the W that fits my data well, right, is a good linear fit for the data X and Y that I have, right, but is also small in magnitude. Okay, so I don't want my W's to take on these like crazy large values, right? I want it to be reasonable values, right? But I also want it to fit the data well. And how I trade off between those two potentially competing objectives is with this lambda, right? This lambda tells me how much I care about each one of those objectives. So this is what we call ridge regression. Okay, ridge regression is this problem. It's the argmin over my weight vector W of these two norms squared with lambda in the middle as the controlling coefficient. Okay, so this wasn't animated, wasn't very pretty. We can stop here for a second if people want to jot some things down or ask any questions. and then we'll move on if we don't have any. Yes? So L2 regularization versus map, right? It's sort of like thinking about the same thing in two different ways, right? So we can approach it from the perspective of regularizers, right? So L2 regularization is an example of a regularizer that I can add to my loss function. I remember we defined regularizers as, typically something that you add to your loss function that doesn't depend on the data, right? It's something that's independent of the data, such as the magnitude of my parameters. What we're trying to say here is that we can take different perspectives on a lot of different concepts, right? And another perspective that we can take on the same concept is the perspective of map estimation, right? And it happens to correspond to map estimation where the prior that I put on my parameters theta is this MVG. And then as it turns out, if we do that, then we work out the exact same thing that we would get if we used L2 regularization, right? One of them comes out to like 1 over 2 sigma squared. The other one is just like a lambda, right? But we can just set these two things equal to each other, and then we get the exact same thing. Does that kind of make sense? Yeah. Yes? Yeah, that's a great question. So, strictly speaking from a probabilistic perspective, we would imagine that we would choose P of theta in such a way that we actually believe that that's like the real distribution that my parameters come from, right? That would be like the Bayesian perspective on things. In reality, we make a lot of these simplifying assumptions, and we also make a lot of compromises because maybe the real P of theta that I want to specify is just like way too complex, right? Like maybe it's just something that I have no hope of optimizing over. Therefore, it's not a good practical choice because even if that's the true P of theta, there's no way that I'm ever going to be able to solve my problem, right? So we make this simplifying assumption, and it turns out, this MVG turns out to be a really simple one that a lot of people use just because it's so easy to do optimization with it. Does that kind of make sense? Yeah, that's pretty much correct. So, map estimation says you should specify P of theta, and if we were, if we were purists, we might say, well, we really want to specify P of theta that's as close to the true distribution as possible, whatever we believe the true distribution is, right? But then we make these simplifying assumptions, say it's like an MVG, whatever, and then out pops, ridge regression or L2 regularization in general. Okay, so let's work this out, actually. So let's solve ridge regression. And this might be, a review for some of you. If you've never seen this before, that's also okay. Hopefully, it's, relatively easy to follow along, but, we'll take it slowly. So our objective, you remember, right, was the following minimization, right, where we had, didn't lose much. Following minimization. Oh, that's the problem. Okay, let's hope that this doesn't do that again. Okay, so our objective, you remember, is the following minimization, right, over my weight vector W of the two norm squared. Does everybody remember what X and Y are in this case, by the way? So remember, X is the design matrix, right, where every row is a data point that I have, right? It's like X1, X2, X3, all the way down to Xn, right? And then Y is another vector, right? That's like Y1, Y2, all the way down to Yn. It's all of my data points, my training data points, right, collected into this matrix vector form that makes it easier to work with, right? So I have this thing plus lambda, right, times the 2 norm squared of my weight vector. So let's rewrite this slightly because it's going to be a little bit easier to work with, right? So we can expand this out. Remember, a 2 norm squared is the vector transpose itself, right? And using that, it's going to be a little easier to write these things out. So what is xw minus y transpose xw minus y? Well, I can use FOIL, right, and just expand out all these different terms. And if I do that, then the first term that I get, right, is this thing that looks like w transpose xw. And then I get, you know, outside, which is like w transpose x transpose y, inside, which is like y transpose xw, but those two are actually the same thing, right, because they're scalars, and so the transpose of each other is the same, right? So I can combine those into a single term that looks like minus 2y transpose xw, right? And then I get like a y transpose y, right? That's the last in FOIL, the L in FOIL, right? So I get a y transpose y, but that thing doesn't depend on w. So let's just throw it away because it doesn't have anything to do with what we're doing anyway, right? And then this thing over here, it's a lot simpler, right? It's just w transpose w. So then I get plus lambda w transpose w. Okay? So then this becomes the minimization problem that I'm working with. If you're not sure how I got from this thing on the top to this next thing, it's a linear algebra exercise, and it's good to be able to do it on your own. And so if it's a little confusing, it's a good exercise to work out. Okay? I'm going to go ahead and write this slightly differently. So you'll notice here what we have are two things that look like w transpose w. Right? We have this last term, and then this thing is like a w transpose w with something on the inside, right? Well, we can actually think of this one also as having something on the inside. It's just invisible. It's an an identity matrix, right? So in that way, what we can actually do is we can combine this term and this term together. If we do a little, dimension matching, it's basically the way that everybody does anything in linear algebra, right? So we have an argmin over w of w transpose x plus lambda, okay, and we're going to put an I in here, right, to make the dimensions work out, w minus 2y transpose xw. And so I claim, right, that this term right here, okay, is the same as this plus this, okay? And if that's a little bit confusing, well, it's also another good exercise to try to figure out on your own. But this is just a little bit of linear algebra manipulation to put the first term and the last term together into a single thing, okay? So now that we have it in this form, what we can do is take a gradient and set it equal to 0, okay? So if I take a gradient with respect to my weight vector w, right, then what do I get? Well, this is a quadratic form in w. So if you remember the formula, and you can also look it up in the matrix cookbook, if you look up the formula for how to take a gradient of this quadratic form, what it'll tell you is that you need something that looks like 2 x transpose x plus lambda I w. That's the gradient of the first part. And the gradient of the second part, well, this is a linear function in w, right? So the gradient is a little bit easier. It's just 2x transpose y. Okay? So here's my gradient, right? And I'm solving for the map estimate, right? So I'm saying that, the map estimate will satisfy that this gradient is equal to 0, right? So for the map estimate, so for w map, right? That's a subscript that I'm trying to squeeze in there. There's not a lot of room. But for w map, this thing, no. Why does this keep happening? Let me rewrite the critical thing up here, which is that the problem that we have, right, is x transpose x plus lambda I w minus 2y, 2y transpose xw, okay? And the gradient, you remember, was 2x transpose x plus lambda I minus 2x transpose y. Oh, I forgot a w. You need that thing. Remember, and for the map estimate, w map, right, what we're going to get is that this thing equals 0. Okay, so then if I solve this, right, if I divide by 2, move x transpose y to the other side, and then multiply by the correct inverse, right, then what I'll get is that the map estimate is equal to x transpose x plus lambda I inverse x transpose y. Okay, don't glitch out on me. Okay. So, I had previously asked before who's seen the least squares linear regression solution, x transpose x inverse x transpose y. It was a lot of people. How many people have seen this solution, the ridge regression solution? Fewer. Okay, that's cool. So here's something new for you. Okay, so this solution, you might notice, looks a whole lot like the least squares linear regression solution, right? What's the thing that's different? Well, the only thing that's different is that we put this lambda I inside our inverse, right? And there's actually a number of ways that we can interpret this, and we're going to interpret it on the next slide, or do some amount of interpretation on the next slide. But that's basically the only difference. Everything else is the same as the solution that we found for least squares linear regression. It's just that now we put this lambda I on the inside. But it's kind of cool that there's still this like closed form solution, right? Yes? Why can you assume that x transpose x plus lambda I is invertible? Yeah, that's a great question. So x transpose x, right, is x transpose x is a PSD matrix, and then I claim that adding any positive lambda along the diagonal is going to make that thing fully invertible. Maybe numerically it's still difficult if lambda is too small, but I claim that that's always going to be the case. That actually is a great segue into this next slide. So the ridge solution differs in adding this lambda I term inside the inverted expression, right? So let's take a second and think about what does this actually do when we do that? Well, intuitively, right, it makes the resulting solution smaller in magnitude, right? Because we're adding something that's inside an inverse. And the inverse is basically like a division, but like, you know, a multivariate linear algebra version of a division, right? So we're dividing by a bigger number, which makes the resulting solution smaller. And that's exactly what we think should happen, right? Because we're adding L2 regularization. We're trying to make the solution that we get, the parameter, smaller in magnitude, and it turns out that's exactly what it is that we're accomplishing. Numerically, it can fix what we call underdetermined, or even if they're not underdetermined, it can fix ill-conditioned problems. And this is not really something that is going to be the focus at all in this class, but it is a good thing to know about that ridge regression has this nice property compared to least squares linear regression. What do I mean by this? Well, recall that we talked about in a previous lecture last Friday, right, how the least squares solution that we found, it needs x transpose x to be invertible, right, because the solution is x transpose x inverse x transpose y, right? And x transpose x is invertible only when the columns of x, the features that we have, are linearly independent. And if that's not true, right, then we're not going to be able to actually solve for the least squares linear regression solution in that way. However, if we add any lambda I for a lambda that's greater than 0, we're guaranteed that x transpose x plus lambda I is invertible. And even relatively small lambda, think like on the order of 0.01 or 0.001 or something like that, can generally make the problem what we call better conditioned. And an intuitive way to think about conditioning is how easy is it for a computer to solve, right? So computers have like, you know, limited precision that they can perform operations with. And so if your problem is ill-conditioned, then your computer might have a lot of problems with like what we call overflow or underflow or different problems like that. Adding a lambda, even a small lambda, can oftentimes make those problems go away quite rapidly. And I think that this is probably something that either in this homework or the next you're going to explore a little bit. Yes? Right, so if people considered replacing lambda I with a full matrix, that's called Tikhonov regression, and I think that's also something that's going to be on your homework. Yeah. It's not as common for, you know, fairly obvious reasons, like it's more complicated, but it is something that is possible to do for certain matrices. Yeah. Great. So that's ridge regression. Let me go into a little tangent and talk quickly about selecting or setting lambda, right? This coefficient that we have that trades off between the goodness of fit, right? How well my W explains my data, right, versus the magnitude of W itself, right? So how do we actually select this thing that does this trade-off? So think for a minute and then answer if you can. Can we choose lambda the same way that we learn W? So that is, I have my optimization problem, right, where I'm doing an argument over W. Can I also add lambda with the constraint that it has to be greater than or equal to 0? Can I add that to my minimization problem? Yes or no, why or why not? Yes. That's exactly correct. So to reiterate exactly what you said, right? If I do this minimization over lambda as well, the lambda that I'm going to get is 0, okay? Why? Well, if I set lambda equal to 0, then the second term disappears, and then all I have to do is find a W that minimizes the error between my linear predictions and my targets, right? There is no setting of lambda that's positive that would actually be any better for this objective, right? Because any positive lambda that I'm going to set is going to only add some positive number to the objective, right? And I don't want to do that if I'm just doing this minimization. So therefore, this is a really bad idea, because if I try to set lambda according to this minimization, all I'm going to be doing is setting it equal to 0. That kind of makes sense from a training perspective, right? From a training perspective, if all you care about is fitting the data that you have, then why would you worry about this type of regularization at all? We add regularization not for the loss on the data that we're given. We add regularization because we think that it might do a better job, right, at generalizing to data that we haven't seen yet. That's the whole point of regularization, right? And so we're going to talk a lot more about that in the coming weeks. But just as a teaser of what's going to be coming, what we call lambda is a hyperparameter. Okay, so we can call W the parameters. To distinguish W from lambda, we'll call lambda a hyperparameter. And basically what that means is that lambda is a parameter that we set. We don't learn it, okay? And we set it ourselves using a procedure called validation, which is going to be an extensive topic for future weeks. If we learn hyperparameters with the same objective, what we're oftentimes going to see is that we're overfitting, okay? Like in this example, lambda gets set to 0. All of a sudden, all we care about is fitting the training data, right? And this can be prone to this problem that we call overfitting, where we do good on the training data, but then on new data that we're trying to generalize to, we do crappy. And that's the kind of situation that we want to avoid. Therefore, we have to avoid trying to set lambda on our training data. And like I said, in a few weeks, we're going to talk a lot more about how to actually select these hyperparameters. This is just a preview of what's to come. So then let's leave ridge regression behind. Okay, we found the solution there. That was cool. L2 regularization, still pretty simple, right? And we could just add a lambda I inside our inverse and still get a closed form solution. Nice, right? That was cool. But there are a lot of different, from the map perspective, right? There are a lot of other, different P of thetas that I could imagine, right? P of theta as an MVG is really only a single choice, and there's, a lot of different choices that people have played around with. So let me tell you about another one, where from the map perspective, what if we set P of theta to be this Laplace distribution? Remember, we talked about the Laplace distribution, right, when we were talking about least absolute deviations, linear regression, rather than least squares. But I'll give you a little, a refresher on what the Laplace distribution is and how it applies here. So if my P of theta I, right, so I is like every dimension in my parameters. Okay, so I'm going to write out this distribution across every dimension. So maybe I should also add a note here that P of theta, the vector, is going to be equal to the product over all of my dimensions. So let's say that theta is d-dimensional, right? Because my data is d-dimensional and I'm doing linear regression, right? Of P of theta I. So all this is saying is that I treat each dimension in my parameters as independent, at least as far as the prior is concerned, okay? So if I set each one of these dimensions to be a Laplace, right, well, the Laplace looks like this. P theta I is equal to 1 over 2b, right? B is this parameter that I have here, right? So 0 is the mean of the Laplace, and b is, what we call like the deviation, times an exponent, because we like exponents, of the negative of the absolute value of theta I. Here there's usually like a minus the mean, but the mean is 0, right? So it's just this thing. Why does this keep happening? P theta I is equal to 1 over 2b exponent negative absolute value of theta I over b. Okay, here's how the Laplace distribution is defined. It looks pretty similar to a Gaussian, right? The Gaussian had like a square inside the exponent. This thing has an absolute value. That's pretty much the only difference. What is log p of theta I? Well, this thing is equal to, negative 1 over b, right, of the absolute value of theta I. That's the thing that was inside the exponent. I just, removed e to that because I'm taking a log, right? Minus log 2b. That's the normalizing constant out front, right? And you'll notice that this thing is my favorite thing. It's a constant with respect to b, or sorry, with respect to theta. Not a constant with respect to b. It's a constant with respect to theta, which means that eventually we're going to be able to get rid of it entirely when we do our optimization over theta, right? Because it doesn't have anything to do with theta. So let's take a look at what map estimation looks like in this particular setting. So let's switch back to argmax. You might be wondering, why am I switching back and forth between argmax and argmin all the time? It's because I want you to be familiar and comfortable with both of these different formulations. Okay, they're very similar, right? One is just the negative of the other, but you're going to see both. So it's important to be able to, sort of identify what it is that you're looking at and making sure that everything makes sense to you. So here, right, the map, right, is the sum over all of my data. Oh, I can't use I anymore. I already used I. Why did I use I? Should have used J or something. Okay, well here I'll use J for my data. Doesn't really matter what letter I call it, right? It just has to be different than what I used before. We'll see if we can fix this in the future. I don't know why this is happening, actually. I hope everybody wrote down what the Laplace distribution is. But maybe, look over at somebody else's if you missed it. So sum over all my data points, right, of the log p theta of yj, here I'm calling it j, right, given xj and theta, okay? And I have this, plus, I have a log p theta term, right? But remember, p theta that we've defined here is a product over all the different p theta i's, right? We're treating each dimension of my parameter separately. And so if I take a log of that, then the thing that I get is a sum, here I'll say I, over all my dimensions, right, of the log p theta I. Okay, this is my map formulation, right? So let's actually write this out. Now let's switch this into an argmin, and I'm gonna call theta w, because that's what I do in linear regression. Okay, so I'm switching multiple things simultaneously, but hopefully it's clear to everyone how I'm doing these switches, right? Nothing too complicated. Of the following. So it's the sum from j equals 1 to n. This first term right here, log p of, shouldn't have wrote theta here because I already wrote theta back there, right? Log p of yj given xj and theta, right? In linear regression, right, where I assume this Gaussian of y given x, right? That whole thing we've already seen turns into xw minus y, 2 norm squared, right? And as an exercise, it's good to go back and review, how did I get that? It's going to be, good to know that, you can do that on your own if you need to. Although, for the purposes of right now, just memorizing it is fine. And then this outer term right here, right, based on the Laplace distribution, turns into something that looks like 1 over b, okay, sum from I equals 1 to d of the absolute values of theta I, of all my dimensions. Okay. Can anyone tell me what is this right here? Yes. That's exactly correct. This is the L1 norm, right? At this point, you might be thinking, well, I mean, Marvin, you picked the Laplace distribution because you knew it would lead to the L1 norm. That is partially true. Sometimes, what we're doing is we're just, we're interpreting choices that we've already made. It's, quite common that you might say, well, what I want to do is use L1 regularization. Well, as it turns out, we can interpret it as map in this particular formulation. It goes both ways, right? We can go from regularization to the map perspective, or from map to the regularization perspective. It's good to be able to be familiar with both of these perspectives because you can start from either one and then maybe relate it to the other and come out with something that's simpler or easier to reason about or more intuitive or something like that. Okay. And again, just as a note, right, from this perspective of minimizing a loss function that has a regularizer on it, right, this time it's L1 regularization, we can replace 1 over b with some lambda. Now, it's not going to necessarily be the same lambda that I had before. Well, but the point here is that we can replace 1 over b with just some coefficient that we control. Okay, that's like the loss function regularization perspective. And the map perspective would be controlling b, or picking b, or figuring out what the right b is. Okay? Everyone's still with me? So it looks quite a bit like ridge regression, right? We just replaced this, L2 norm squared regularizer with an L1 norm regularizer. That's basically all we did here. Okay? So this is what we call lasso regression. Okay, so lasso regression is regression where we have L1 regularization, lambda, times the L1 norm of my parameters. And what's cool about this actually is that L1 regularization compared to non-regularized problems and also compared to L2 regularization tends to lead to what we call sparser solutions. What do we mean by sparse? It means that it's more likely that some of my parameters will be set to 0. Okay? So I'll have fewer parameters that are non-zero. As compared to something like L2 regularization, it shrinks everything towards 0, but it doesn't usually make things 0 exactly. L1 regularization is a bit more like actually pushing things towards 0 exactly. That's the difference between these two regularizers. And so, did this already play? Play this again. Will this play? No? There we go. Yeah. Here's a cool visualization of L2 regularization versus L1. It's basically as you move, the distribution of the data that's being generated. What is the best set of parameters that you can find, which is that yellow dot? And what you can see is that for a lot of different settings of this problem, L1 regularization has optimal parameters, yellow dots, that are along a particular axis. Right? If it's along an axis, that means that the other parameter is set to 0, and it has very few or fewer, right, where it's not actually along an axis. And then for L2 regularization, you can see that most of the times it's not actually along an axis, which means that both of these parameters are going to be, non-zero. They just might be small. Is kind of the difference here. This is not exactly the perfect visualization, but it gives a flavor as to what's going on with L1 regularization inducing sparser solutions. Yeah, in the back first, and then we'll take here. Yes, okay, yes, this is too small. Yeah, the graph on the right is L2, and the graph on the left is L2. and then the right is L1. And these slides will be posted later too. Yeah. That's like the, well, okay, so that was a bit of a abuse of language. The ovals are like your non-regularized loss function, okay? So these axes represent your parameters. So here we have two parameters, theta 1 and theta 2. The ovals are like level sets or contours of the loss function, but that's just the part of the loss that's like how good are you fitting the data, right? So this center of the oval, that represents the unregularized solution that you would find, just from least squares, right? And then basically, we're going to add something that makes it such that we actually move closer to this region, right? Which is either a diamond for L1 regularization, or it's a circle for L2 regularization. And that's just like the difference between L1 norm and L2 norm, right? And so basically, the center of the oval, the center of the ellipse is our unregularized solution, and then we have a regularized solution, which is like the loss plus lambda times the norm. And as it turns out, the way that this plays out is that most of the time for L1 regularization, we're going to be along a particular axis where the other parameter is set to 0. But for L2 regularization, that's usually not the case. It's just that all the parameters are small, but they're rarely ever non-zero. Yes. Exactly, right? So as your lambda gets smaller, you can think of these blue regions as getting bigger because you're not as constrained to lie close to the origin, right? But this is a good visualization, but I would say that it doesn't perfectly correspond to these problems of regularized loss functions, because this is getting a little bit in the weeds. But the blue region to me looks a little bit more like a constraint set, right? Where we'd say that we need the solution to fall in that range. It's not exactly what penalized regression is, but anyway, I think that this is still like a good visualizer of how these two regularization schemes differ. On the right here, okay, we have a problem solved with both ridge regression, L2 regularization, and Lasso, L1 regularization, okay? And the main difference is that we're visualizing here like this is tiny, sorry. So on the x-axis is how big is your lambda? Okay, so as your lambda grows, you're pushing your parameters towards 0, right? On the y-axis, we're actually visualizing these different parameters that we learn, okay? And the parameters, they're going towards 0 as we increase lambda, right? Because that's what regularization does. But what we can see is that for L2 regularization, they kind of start shrinking towards 0, but they're never exactly 0. They actually, sort of hover around this non-zero regime that's very small for a long time. Whereas for something like L1 regularization, basically it goes down and then it just hits 0, and then it just stays there. Okay, so that's the difference, is that L1 regularization is better if you want sparsity, which means that maybe you believe that you collected too many features, right? You measure too many features, and you don't think that all these features actually matter, right? So if you think that not all features actually matter and you only want a subset as part of your prediction, then L1 regularization makes a lot of sense, right? Because that's basically saying, I want a lot of my coefficients to be equal to 0, and I want to find only the subset of features that actually matter, right? That's the intuition behind L1 compared to L2. Yes? Yeah, that's a really interesting question. So, can L1 sort of compensate for doing feature selection yourself? In a sense, it can, right? It is kind of automating that process. You still have to select things like lambda, right, which is going to control how many non-zero coefficients you have, how many features you care about, right? But it is sort of a different take on kind of automatically extracting the features that matter rather than having to do it yourself. Yeah. The problem with lasso regression, I've talked about good things, right? The problem with lasso is it doesn't have an analytical solution, So the thing that I wrote, the optimization I wrote on the previous slide, I can't just take the gradient and set that equal to 0. Well, actually, I can. I can take the gradient and set it equal to 0, but out does not pop, a W map, right? There's no W that I can actually read off of the paper when I set that gradient equal to 0. That's the problem, okay? So most commonly, lasso regression is solved with a set of methods called proximal gradient methods, which is not something that we're actually going to cover in this class. But you can learn about those in like optimization courses or stuff like that if you're interested. This is just a note that this is how lasso is typically solved. Okay, I do have 3 minutes, so I think that we can finish up by talking a little bit about featurization, and that'll lead us into next week when we talk about classification. So we're almost done with regression, leaving it behind at least for a little while. And I want to ask the question to start, how powerful are linear models anyway? So we've been talking so much about linear models, right? I'm just rambling nonstop about linear models. Why? What can linear models even do? All they can be is a line, right? How good could that possibly be? Well, linear models by themselves might not seem that useful, right? Because they can only represent linear relationships. However, they can be if we use the right set of features. Okay, so we haven't talked so far about how to actually construct features. We just assume that they're given to us, right? We have some vector x, and that vector contains all the features that we possibly can use. That's how we've been talking about it so far, right? But maybe we can do better. Maybe instead of using x directly, what we can do is work with a featurization of x. And we're going to denote that mathematically as a function phi that takes in x and then spits out some other representation, okay, some other vector that we call phi of x. Maybe this is actually better suited for the data, and then everything else just stays the same, okay? So everything that we've talked about in terms of linear regression, all of that still applies. What we're going to do is we're just going to replace x with phi of x everywhere, okay? Instead of the original features that we had, now we're going to work with some other set of features that we think might be better for the problem that we want to solve. We're going to talk extensively in this class in the coming weeks about different featurizations, both hand-designed and also learned. And so we're going to do a lot of this. But just to motivate it, let me give you a really simple example that maybe you've seen before. But if not, that's OK. We'll try to explain it intuitively. Here's a classic example. And this example is actually for linear classification, which we'll talk about next week, not regression. But you should be able to get the general idea. So let's say that I had data that looks like this. Okay, I have 2 dimensions to my data, x1 and x2. And then I have 2 classes. Okay, so let's say I have some red pluses, that's one class. And then I have some green minuses. That's another class. And maybe this is the data that I'm given. What is a good decision boundary for this data? What's a good way to classify between these 2 classes? Well, if you look at it, it would be something like this circle. What's the equation of a circle? It's x1 squared plus x2 squared equals some c, right? Here, this is actually not centered at the origin, so I should have some offsets a and b. But let's just ignore that for a second. Okay, this is the general equation for a circle, right? And this is what this is the decision boundary that I'm trying to learn, but it's non-linear, right? So every linear model that we've talked about so far, it's not going to be able to do anything for this. So if I have my feature vector x as x1, x2, it's a non-linear boundary. I can't represent this with a linear model. But what if I chose a phi of x that does a little bit better? Specifically, I can choose phi of x such that maybe it has the original features, x1, x2, but then it has all of the quadratic, 2-term combinations of my features. So I can include x1 squared, x1, x2, and then x2 squared. If I do this, then all of a sudden, this decision boundary, which is a circle, it's quadratic, right? I'm able to represent as a linear function of phi of x. And then all of a sudden, my linear model can do the job that I want it to do, okay? So this is a high-level idea behind featurization, is that we can combine simple models, like linear models, with complex features.